Okay. The last topic we're going to talk about are acid-base titrations, and we're going to do a titration in lab, and we're going to look at some of this, so hopefully it'll become familiar or it is already familiar. So an acid-base titration is a commonly used method of analyzing an unknown of an acid or base. What do? We accurately measure the amount of unknown acid or base and put it in a flask. We add a few drops of indicator, and then we're going to add a base, or if we started with the base, add an acid. We're going to add, and we want to know this, the second one, we want to know the concentration exactly, because what we're going to do is we're going to measure, we're going to keep adding it until the color changes. So we're going to know exactly our concentration and exactly how much of the base we're adding till we get to the end point, and the end point is when the color change happens, and at the end point the amount of acid equals the amount of base. So at the point where all the acid has reacted is called the equivalence point, and this is where moles of acid equal moles of base. So we're able to do calculations. So if you have an unknown concentration of acid but you want to find out what it is, you can titrate with an accurately measured amount of base, and then you can do that calculation. So we already know the concentration of the base, we know how much of the base we used, and so we can find we know how much of the acid we started with, so we can find the concentration of the acid. So this just sort of shows you, if we haven't done it already in lab, you're going to have your unknown solution, but you know how much you have, either by volume or by mass. So I think we'll do a KHP where we measure the weight and put it in water. So the amount of water is not critical, but the moles is the same. Then we're going to add, we have the burette filled with a basic solution, and we know the concentration, and so we're going to titrate. When the color changes, then we know we're exactly at our endpoint, and we know that moles of acid equal moles of base. What you're doing with a burette, as you're reading down, it starts with 0, 0 up here, and it runs down to about 50, but you don't subtract from 50, you just read whatever it is. It's meant to be read downward. So you just start at the top. So this would be 1.00, and this would be 2.00 and 3.00. So you can read it to 2 decimal places because you just want to read the bottom of the meniscus, and you can estimate 2 decimal places. All right, so one thing we're also going to do in lab is we're going to draw a titration curve. So a titration curve is the plot of pH on the y-axis versus volume of added base or acid, depending on what you're titrating with, on the x-axis. And we're going to be able to use that to look at titrations. You can use a titration curve in order to choose the appropriate indicator. And we'll talk in lab, we'll talk about indicators. So the next slide shows a titration curve of a strong acid with a strong base. And what I wanted to point out, a couple of things. What is it? If you're reacting HCl plus NaOH, we're going to get water, and we're going to get NaCl. So if you've got a strong acid and a strong base, our ions are such that this is going to be neutral. So our endpoint will be at pH 7 because the only salt that we have around comes from a strong acid, strong base, so it's neutral. At the equivalence point, then we know that the moles of acid equal the moles of base. The midpoint is called the midpoint. The equivalence point is found by looking for the midpoint of the steepest rise, which you'll see when we show that in a minute. And that pH will change slowly until it gets close to the endpoint, in which case it changes very quickly. And so here's what it looks like. So the pH stays real consistent for a while, and then as you get close to the endpoint, it jumps up. Notice that our equivalence point is the midpoint of the steepest rise. It happens to be a pH of 7 because, again, it's a strong acid with a strong base. You can see this is volume added. They read the pH, and we're going to do that in lab. Read the pH with every addition and plot it. with a titration of a strong acid and a strong base, you can use phenolphthalein as a good indicator. Bromocresol green is a good indicator. Anything that changes in the steepest part is fine. So again, it has a pH of 7 because the salt that is formed does not hydrolyze. So this is what it looks like. A strong acid, strong base. It looks very symmetrical. Like I said, to detect the equivalence point, we use an acid-base indicator. In this case, we can use one that changes between 3 and 11. So any of these, the bromocresol green, the methyl red, bromothiamyl blue, phenolphthalein, thiamyl blue, any of those will work for that one. Phenolphthalein is a really nice one that you can really see visually, so it's often used. One thing you want to be able to do is calculate the pH along the way. So how can we calculate the pH of a solution where 10 milliliters of base, 0.1 molar, is added to, so we start out with 25 milliliters of 0.1 molar HCl, and then we've added 10 milliliters of 0.1 molar NaOH. Should this still be acidic? Should it be neutral? What should it be? And so what we can do is we can find out how many moles of acid we have, compare it to how many moles of base we've added, and we know if the base, if they're equal, we're at the end point. If the amount of moles that we added is less, then we're before the end point. And if the amount of moles of base added is more, then we're after the end point. So the first thing you want to do is calculate moles of acid and moles of base. All right, so remember that moles equals molarity times volume, and volume has to be in liters because molarity is moles per liter. So we want to convert this to liters, 0.0100, and this is 0.0250 liters. So if we multiply 0.0100 liters times 0.1 molar, we have added 0.001 moles of OH. How much HCl have we added? 0.00250. Obviously, we're not to the end point yet because we have more acid than base. So what's happened? Well, when we've added the OH negative, the amount of OH negative that we've added has reacted with an equal amount of H3O plus. So some of the H3O plus has decreased because we've titrated some of it. Also, we've diluted it. So two things are happening. The concentration of OH negative has gone down, first because we've titrated some, second because we've diluted it because we've added more volume. So what we can do is figure out how many moles of H3O plus we have left by subtracting. So if you subtract 0.0025 minus 0.0010, we get 0.00150 moles of H3O left. So like I said, we started with 0.0025 and now we have 0.0015. But also remember that we've diluted it, so our total volume now is 35 milliliters or 0.0350 liters. So to find the concentration of H plus, we divide by the new volume. And so our new concentration, it started out at 0.1 molar, but now because of titration and dilution, it's now 0.0429 molar, and we can find the pH 1.368. It would have started out, if it was 0.1, it would have started out at 1.00 was the pH to start with. So it's definitely increased, but not very much. So let's look at the next. All right, so let's say we add OH past the end point. Now there'll be more OH than H3O plus. We can use the same process. So let's say we did, actually let me erase that and move it down here. Let's say we had 0.0035 moles of OH negative added. So then, and we had the 0.00250 moles of H plus. This time we know we have an excess of 0.00100 moles of OH excess. And then 100,100. This time we have, that would mean 35 milliliters. So we have a total of 60 milliliters, which would be 0.0167 molar. This time it's OH negative. So if we take the log of that, we get POH is 1.78, which means the pH will be 12.22. So again, if there's excess OH, so you have to figure out what you have more of, subtract, figure out how much you have more of, divide by the total volume to get the concentration of whichever one you have more of. On the last slide it was H plus, this time it's OH negative, so then because it's OH negative you can find the POH and then the pH, which should be greater than 7 because we're past the end point. If we are at the end point, OH negative equals H3O plus, and since there's no other ions that can hydrolyze, the pH will just be 7.0. So sometimes people will subtract and you get 0, and you think, what do you do with that? Well, because there's no other ions, then the self-ionization of water takes over, and you just say pH is 7 because they're equal to each other. So you're at the equivalence point. All right, now this shows the titration of a weak acid. So if you have a weak acid with a strong base, a couple of things are different. First of all, notice that our equivalence point, or the pH of our endpoint, is greater than 7. Here it is 8.78. So it's got to be greater than 7. Why is that? Because you have the conjugate acid, the conjugate base of the weak acid is hydrolyzable. And so we have to worry about it, and it will, because it's somewhat basic, the solution at the endpoint will be basic. The other thing that we can see is that this, the steepest part is smaller, and this is kind of goes up a little bit less. On the other one, it was more flat, and this one kind of goes up and up. This where it's colored, this is called the buffer region, because you've got some of the acid and you've got some of the conjugate base around. So this is the area where pH is changing slowly, and you can see pH is somewhere around 4.5, and it changes very slowly through this region. It's only if you add too much base, eventually you get to where you're past the end point. So a couple of things to notice: it's not as symmetrical. There's a buffer region, and the pH in this case is greater than 7. So this just shows the two side by side. So a titration of a strong acid with NaOH gives the equivalence point right at 7, and it's much more symmetrical. And the titration of a weak acid has this buffer range. It's much less symmetrical, and the pH is higher than 7. And this is another figure. This is showing you a strong acid, HCl, and then a weak acid, acetic acid, being titrated. And you can see them on top of each other. What this is showing is proper acid-base indicator. So, you know, if you use methyl orange on a strong acid, strong base might be okay. It's going to change color just in the range where it just starts to change. So it's probably not horrible. But if you use methyl orange on a weak acid, it's going to change colors way before the end point. So you always want to pick an indicator that changes close to the end point. Now again, the phenolphthalein on the strong acid, strong base is probably okay because it's still sort of in that region, but phenolphthalein would work perfectly for the weak acid, strong base, but methyl orange won't work at all because it changes at too low of a pH. So you have to pick the right indicator. All right, so how can you find the pH at the equivalence point? Well, this is actually just similar to a salt problem, because what you have left over is the negative ion of the acid, because that's all that's around at the endpoint. Technically, it is a salt, because if you take, say you take acetic acid and you titrate it with NaOH, what do you have left over? You have sodium acetate, which is a salt. So this is really just a salt problem, but we can ignore the sodium because it comes from the strong base. So we're gonna find out once the titration occurs, this is all we have left, and the only thing we have to be careful about is the volume, because there's going to be a new volume because we're titrating. So calculate the pH of a solution at the equivalence point when 25 mils of 0.1 molar acetic acid is titrated with 0.1 molar sodium hydroxide. So this is a little bit more tricky. So it's basically your salt problem, but we don't know the concentration of the salt yet because we have to figure out the volume. So we know the moles of acid that we started with, because it's just volume times molarity. And we know the concentration of the base, so we can find out how much base we need to add to get to the equivalence point. So that's the first thing we have to do. So like I said, at the equivalence point, only the sodium ion and the acetate ion are present. We can ignore the sodium. And so the pH will depend on the acetate ion. So this is our Kb expression, our base, the salt that's left over at the end of the titration will give us OH negative, and we can find the pH once, because we can use Kb. Kb equals OH negative divided by C2H3O2. Now, the problem gives us the Ka, but we do know that we can find the Kb from the Ka. But what we need to know is what is the concentration of this. So we can use an ice chart to find the pH once we know the concentration of the acetate. So the first thing we have to do is figure out how much NaOH we added. The moles of acetate are equal to the moles of acetic acid, since that was what was titrated. So 0.025 liters of acetic acid is 0.0025 moles of acetic acid. So that means there's 0.0025 moles of the acetate ion after the titration. Since the moles of acid equal the moles of base at the equivalence point, that means we had to have added 0.0025 moles of base. We know the concentration of the base, so that means we added 25 milliliters. Now in this case, we started with 25 milliliters and we titrated with 25, and that's because they're the same concentration, but they can be different concentrations, so you have to be careful with that. In this case, because they were the same concentration, you could already tell it was 25 milliliters, but this is how you would find out if it was a different concentration. So we added 0.025 liters of NaOH. So that means our total volume is 50 milliliters, or 0.050 liters. So the molarity is the moles of the acetate divided by the new volume, 0.050 liters. So not only did you titrate it, you also diluted it. So the concentration of the acetate ion is 0.050 molar. Now we can set up our ice chart. So 0, 0 minus x plus x. And again, it's Kb equals x squared over 0.050 minus x. However, we don't know the Kb. We only know the Ka, but we can find the Kb because Kb equals Kw over Ka. So that's my Kb. So now we can solve. Kb equals x squared, and we're just going to assume x is negligible because this is so small. We can do that. So, or Ca over Ka, or Cb over Kb is going to be way more than 100. So we can ignore our x minus x. So x equals 5.4 times 10 minus 6, and the pH is 5.27. Oh, sorry, POH is 5.27, so our pH, I was just thinking that doesn't sound right. So because it's a titration of a weak acid with a strong base, our pH should be above 7 at the endpoint. So that's what it is. It's easy to find the pH of a titration of a weak acid strong base at the halfway point to the end point, because I sort of mentioned this earlier, because at the halfway point, half of the acid has been titrated to base, and so the two concentrations are equal. And remember, according to the Henderson-Hasselbalch, if these are equal to each other, that ratio is 1. The log of 1 is 0, so pH equals pKa. And so on that last problem with acetic acid, the halfway point, if we titrated acetic acid with NaOH, the pKa would be negative log of 1.7 times 10 to the minus fifth, which is 4.77, so the pH would be 4.77 in that last example. Which makes sense, and then it's greater than 7 at the endpoint. All right, just one more thing. If you're titrating a weak base with a strong acid, you're going to see the similar type of structure. So again, you've got your buffer region up here. pH will start high because it's a base, and it will decrease. And then again, you have your endpoint. This time, your endpoint is going to be less than 7 because you have the conjugate acid of your weak base. So we're not going to do any calculations with this, but you can recognize it. The pH will be less than 7, and it will not look even. If you did a strong base with a strong acid, it would look just completely opposite. It would be very symmetrical. All right, in this case, methyl red would be a good indicator. All right, that was a whole lot of stuff. What should you be able to do in this chapter? You should be able to identify a Bronsted acid and a Bronsted base in a reaction, decide which is acid, which is base, decide whether reactions or products are favored if you know which one's stronger from the chart, determine which acid is stronger based on electronegativity and structure, meaning those binary acids, oxo acids, just comparing within the same column or row of a periodic table. So I couldn't ask you anything. It would have to be in comparison. Be able to calculate the concentration of H plus and OH negative if you know the strong acid or base. Be able to calculate the pH if you know the H plus or the OH negative. Be able to calculate H plus or OH negative if you know the pH. Determine Ka or Kb from the solution if you know the pH. Those were some of the early problems that we did. Calculate the pH if you know the Ka or Kb. I think that's the next one. Calculate the concentration of species and the pH for a weak base if you know the Kb. Predict whether a salt will be acidic, basic, or neutral. Be able to find Ka from Kb or Kb from Ka. I know when you need to do that. Be able to calculate concentrations of species and find the pH in a salt solution. Calculate common ion effect if you have both acid and common ion base around. Be able to calculate the pH of a buffer using the Henderson-Hasselbalch equation. Be able to calculate the pH of a solution at any point during the titration of a strong acid with a strong base. And be able to calculate the pH at the halfway point and at the equivalence point in the titration of a weak acid with a strong base. So that is a lot for this chapter. Hope you work hard.